What if I told you that most of the universe is made up of something we can't see, touch, or even comprehend? Yes, I'm talking about dark matter. Imagine venturing into a cosmic jungle, where over a quarter of its mass, precisely 27%, is something entirely invisible to us, known as dark matter. This elusive substance doesn't interact with light like the objects we see around us. It neither emits nor absorbs light, and it doesn't reflect it either. Now, you might wonder how we even know it's there. Dark matter reveals its presence not by a grand spectacle of light and color, but through its gravitational pull. This gravitational force is strong enough to influence the movements of stars and galaxies, holding them together like an invisible glue. Despite its stealthy nature, the effects of dark matter are immense, impacting the very structure and evolution of the universe. So why do scientists believe in something they can't see? Let's dive into the evidence. The story begins in the 1930s with a Swiss astronomer named Fritz Zwicky. Working in the serene observatories of California, Zwicky cast his gaze towards the heavens, specifically targeting the Coma Galaxy Cluster, a massive collection of over 1,000 galaxies located about 320 million light-years from Earth. As he meticulously analyzed the motion of these galaxies, Zwicky stumbled upon a cosmic puzzle that would baffle the scientific community for decades. Through his observations, Zwicky noticed something peculiar. The galaxies within the cluster were orbiting each other at such high speeds that, under the known laws of physics, they should have been flung apart and scattered into the cosmic void. Yet they remained gravitationally bound within the cluster. The gravity exerted by the visible matter in the galaxies was far too weak to account for their unexpectedly rapid motion. Zwicky proposed a bold and revolutionary idea. There must exist some form of unseen matter which he termed dunkle materie, dark matter. This invisible substance, according to Zwicky, exerted additional gravitational forces, effectively gluing the galaxies together in the cluster. Several decades later, in the 1970s, an American astronomer named Vera Rubin provided further compelling evidence supporting Zwicky's theory. Rubin, focusing her research on galaxy rotation curves, discovered that stars at the outer edges of galaxies were rotating just as fast as those near the center, a phenomenon that defied the expectations of Newtonian mechanics. According to the rules of gravity, stars on the outskirts should have been moving slower due to the lesser mass exerting gravitational pull on them. Rubin's findings indicated that each galaxy must be embedded in a halo of dark matter, far more extensive and massive than the galaxy itself. This invisible halo was keeping the stars in their rapid uniform orbital dance. These pivotal moments in astronomy pointed to a clear conclusion. There is more to the universe than meets the eye. How can we observe something that is completely invisible? It sounds like a trick question, doesn't it? Yet this is exactly the challenge scientists face when studying dark matter, a substance that does not emit, absorb, or reflect light. But just because something is invisible doesn't mean its effects can't be observed. Enter the fascinating concept of gravitational lensing. Gravitational lensing is a phenomenon that occurs when a massive object, such as a cluster of galaxies, bends the path of light coming from a more distant object, like a galaxy or a star. This bending is due to the intense gravitational pull exerted by the mass of the object in the foreground. Imagine light as a river flowing through space. As it encounters a massive object, it bends around it, much like water flowing around a boulder. This cosmic phenomenon acts much like a lens, hence the name. It magnifies and distorts the light from those distant stars and galaxies, allowing astronomers to observe the effects of dark matter even if they can't see the dark matter itself. By examining how the light is bent, scientists can map the distribution and concentration of dark matter between us and the light source. One of the most striking examples of gravitational lensing is observed in the Bullet Cluster. This cluster is actually two clusters of galaxies that have collided. The collision's aftermath provides a spectacular demonstration of dark matter's influence. While the visible matter in the clusters, detected through normal light, interacts and slows down, dark matter does not. It passes through without interacting except gravitationally. This separation is visible due to the gravitational lensing effect, where the light from galaxies behind the cluster is bent around both the visible and the dark matter, outlining the presence of the latter. Through this cosmic bending of light, dark matter reveals its presence, showcasing the power of gravity. This invisible component of our universe might elude direct detection, but its gravitational signature is unmistakable, proving once again that sometimes what we cannot see can still be thoroughly understood through its influence. Dark matter doesn't just lurk in the shadows, it plays a foundational role in the cosmos. Picture the universe as a vast construction site. Here, dark matter isn't merely a bystander, it's akin to the scaffolding around which everything else is built. But instead of steel beams, this scaffolding is made from something completely invisible and immensely more mysterious. Imagine a web stretching across all of space, a kind of cosmic superstructure. This isn't a web of silk or steel, but of dark matter. Scientists, using advanced simulations and astute observations, have discerned that this dark matter forms a colossal web that connects galaxies across millions of light years. The gravity of this dark matter draws in regular matter, helping galaxies to form, grow, and cluster together in the vast emptiness of space. This framework is not random, it's a beautifully complex network of dense nodes connected by filaments. These nodes are where you find the greatest concentration of galaxies. It's as if dark matter is the maestro, conducting an orchestra of cosmic proportions, guiding the movements of galaxies and clusters in a symphony of creation and growth. Moreover, this invisible web tells us why galaxies are not scattered randomly across the universe, but instead come together in groups and clusters. It's this dark matter that orchestrates these gatherings, influencing the gravitational pull and ultimately the structure of the universe itself. This ghostly matter shapes the very architecture of our universe. Armed with knowledge, scientists are not just sitting back. They are on a hunt. In the depths of former mines and buried under mountains lie some of the most sophisticated detectors on Earth, designed specifically to catch a glimpse of the elusive dark matter. Consider the large underground xenon experiment, nestled nearly a mile underground. Here, in the quiet darkness, a tank filled with liquid xenon waits patiently. The theory is simple yet profound. Should a dark matter particle collide with a xenon atom, it will emit a flash of light, capturing a moment of interaction with the invisible. But the search doesn't stop underground. It extends far beyond the confines of our atmosphere. Space-based observatories scan the cosmos, attempting to detect signals or anomalies that could hint at the presence of dark matter. These high-flying laboratories look for evidence in the behavior of galaxies or the distribution of cosmic radiation, piecing together clues from the vast silence of space. Yet the very nature of dark matter makes these experiments extraordinarily challenging. Dark matter does not interact with light, making it invisible and undetectable by conventional means. It interacts weakly with other matter, so rarely does it leave a trace. This ghost of the cosmos passes through ordinary matter as if it were not there at all. Each experiment must therefore be incredibly sensitive, capable of detecting events so rare and subtle that they could easily be drowned out by the noise of the universe or the Earth itself. Moreover, the innovation in technology required to even attempt these detections is monumental. Every sensor, every piece of equipment must be engineered to unprecedented levels of precision and sensitivity. The environments for these experiments are controlled obsessively, as even a stray particle of cosmic dust could skew the results. In this high-stakes game of cosmic hide-and-seek, patience and persistence are virtues. Each experiment, regardless of its outcome, peels back another layer of the universe's deepest mysteries. Every failed experiment and every new theory bring us closer to unveiling the secrets of dark matter. You might wonder, why all this fuss about something invisible? Well, dark matter, despite being undetectable by traditional means, holds the cosmos together, influencing everything from the smallest galaxies to the largest cosmic structures. It's like the scaffolding of the universe, unseen yet indispensable for its construction and stability. Understanding dark matter is not just about filling in the blanks of a cosmic puzzle, it's about comprehending the full picture of the universe, including its origins, structure, evolution, and ultimate fate. Without this understanding, our picture of the universe remains incomplete, like trying to understand the human body without knowing about bones. Imagine the universe as a grand symphony. Visible matter like stars and galaxies are the notes that we hear. But dark matter? It's the silent pauses and spaces that give structure and meaning to the music. Without it, the symphony would lose its beauty and coherence. By studying dark matter, we're not just learning about what things are, but how they come to be, and how they change. This enigmatic substance also challenges and enriches our understanding of fundamental physics. It hints at new physics beyond the standard model, possibly new particles or forces that have yet to be discovered. Each hypothesis and finding about dark matter nudges the boundaries of human knowledge further, promising revolutionary insights into the fabric of reality. By chasing the shadows, we learn more about the light.